All right, yeah, thank you for the introduction, and I'll add my thanks to the organizers for putting together this really awesome workshop. I've been learning a lot. So today I will be talking about periodically driven systems. So I'll be discussing some work that should be appearing on the archive soon about trying to make a connection between sort of Floquet insulators, topological and otherwise, and sort of discrete time lattice Fermion theories. And the reason why I'm doing this is that I have a colleague, Srimoy Sen, in the nuclear theory group at Iowa State, who is interested in sort of topological effects in nuclear matter and in condensed matter. And this sort of project was a way of kind of learning how to sort of talk about interesting things together. And also her student Lars Sivertsen did a lot of work on the project. So at the risk of belaboring something that many people know, I just wanted to review Floquet systems a little bit. So Floquet systems are periodically driven quantum systems whose Hamiltonian depends on time with some period capital T. And instead of analyzing this sort of time-dependent Hamiltonian, often what we're interested in is or can be extracted from the Floquet unitary, which is basically the evolution operator over one period, defined in the usual way. And then, of course, this thing being a unitary has a Hermitian generator that we call the Floquet Hamiltonian. You get it by taking the log. And physically, what does the Floquet Hamiltonian do? Well, it's the generator of stroboscopic dynamics. So what is stroboscopic dynamics? It's essentially describing what happens if you observe the system at times that are integer multiples of the period. And we've seen pictures like this before in our lives, and they're very fun. So the sort of spectrum of this generator is called quasi-energy, and it's only defined modulo 2 pi because energy itself is no longer conserved due to this time dependence, and it's actually that sort of periodicity of the quasi-energy spectrum that allows for novel spectral properties like the ones that we heard about in our pedagogical lecture a few days ago. So, for example, this is an early work. The thing that's interesting here is that you can have systems where the sort of Chern number that you would compute using eigenstates of the Floquet operator, the sort of static topological invariant is 0, and yet you find edge states, right? So you can have an edge state crossing the quasi-energy gap around 0, and then also because your spectrum is periodic, you have a new gap at pi over t, where you can also have edge states, right? So these are sometimes called anomalous edge states. So from this, you might imagine that driving can enable sort of new phases, both ordered and topological in nature. So one that you may be familiar with is this sort of kicked Ising slash Majorana chain, which is a very, very useful model to show things sort of simple calculations. So it's basically a two-stage drive. So you can write down the Floquet unitary directly. You have sort of two Hamiltonians, H0 and H1. You evolve with H0 for a time T0, H1 for a time T1, and then the total period is T0 plus T1. And then, what are H0 and H1? You can, formulate this in sort of spin variables. And in this case, H0 is some paramagnetic Hamiltonian and H1 is some Ising Hamiltonian. One interesting fact that's related to dual unitary circuits, which you heard about last week, is that there's a Kramers-Wanier duality relating these two Hamiltonians. And so, you can imagine that you may have some self-duality appearing somewhere in the phase diagram. This is related to that. And then, of course, you can always do a Jordan-Wigner transformation. And then what you find is that the system can be rewritten in terms of Majoranas. And in this case, H0, you would call sort of the topological, the trivial Hamiltonian in the sense of like a Kitaev chain where you hybridize Majoranas within a unit cell, or H1, which is sort of the topological Hamiltonian that hybridizes Majoranas between unit cells. And then you can sort of, from this picture, you can extract actually analytically the phase diagram it looks something like this as a function of the parameters T1 and T0. And there's sort of 4 phases that come out. I'll explain what they are in a minute, but if you're wondering, what is a phase? This is a question that comes up. Well, in the non-interacting model, so for example, if you just have this picture here, you can diagnose phase boundaries by looking at where the quasi-energy gap closes. So this is some two-band model, and you can just ask, where does my gap close? It closes along these 2 lines. Okay. When you add interactions, of course, things become much more subtle, and then you encounter heating, and you need to sort of try to counteract that with things like, many body localization or pre-thermalization, and to get something that's sort of long-lived. I won't say anything about whether it's infinitely long-lived. But in this case, with interactions, you can sort of diagnose these transitions using, for example, correlation functions. So what are these phases? What do these pictures mean? So let's fix for a moment the Majorana picture, okay? So if we're working with this Majorana Hamiltonian or Majorana unitary, we can distinguish these 4 phases by their sort of edge structure. So there's a trivial phase where you have no edge states. So in this case, this sort of H0 is much stronger than H1. And then there's also what we call the 0 phase. So in this case, there is an operator at, say, the left edge that we call gamma 0, which potentially up to some exponentially small finite size corrections commutes with the Floquet unitary. So this is very similar to strong 0 modes in Hamiltonian systems. And what's common between these 2 phases is that they're both kind of adiabatically or rather smoothly connected to static phases. So you get this phase at small T0, and you get this phase at small T1. They're essentially the same as sort of equilibrium counterparts. And then these 2 are different, right? So perhaps the more famous of the sort of Floquet phases is this pi phase. So what happens here is that instead of getting an operator that commutes with your Floquet unitary, you get an operator that anti-commutes with your Floquet unitary, again, potentially up to exponentially small finite size corrections. And here you have not a Majorana 0 mode, but a Majorana pi mode. So you have a Majorana operator, which is kind of flipping a sign each period. And this thing is sort of Jordan-Wigner dual to a discrete time crystal. So this is the sort of, you could think of this in the spin model, this would be the time crystal phase. And then there's this 0 pi phase where you have both a 0 mode and a pi mode localized at the edges. And there are some reasons why these things don't hybridize and gap out. And so these 2 phases are the sort of intrinsically Floquet phases, you could call them. They have these pi modes, which are living inside the gap at pi, which is not really a meaningful thing to have in a static system. So the one way that we think about Floquet systems, as I said before, is to consider stroboscopic dynamics. You consider dynamics of your, say, system of qubits or your system of fermions that's just generated by repeated application of this Floquet unitary. And so when you measure something, you measure it at these sort of integer time slices. And in this sort of stroboscopic picture, quasi-energy acquires some kind of analogous role to crystal momentum in space. So this sort of periodic variable of quasi-energy is kind of like a crystal momentum in the time direction on a time lattice with period capital T. And then there's an interesting question which arises if, for example, you have a nuclear theory colleague interested in topological stuff and you're telling them about these phases, which is, well, nuclear people discretize time all the time. Right? They do this essentially for a living because you want to study, non-perturbative strong interaction effects, QCD or whatever. And, to make progress, they work on a, space-time lattice, right? So you can take the Schrodinger equation and you can just replace your continuous time derivative with this discrete time derivative. This is a symmetric derivative actually because you want this full operator, the Schrodinger operator, to be Hermitian, right? So you need this symmetric difference to do that. But this is also a way of discretizing time. And then there's sort of a question that arises, which is, how similar is this sort of stroboscopic picture and this sort of discrete time picture? How similar? They kind of seem similar because here, when you discretize, you'll also get sort of a crystal momentum in the time direction. But are they the same as quasi-energies? Are they different? And how similar they should be is not obvious. For example, in Floquet systems, the actual micromotion within a period is sort of what you need in order to diagnose bulk topological invariance. So, you know, it's not obvious that these two things are necessarily the same. So let me review a little bit, you know, what happens when you put, you know, a system, say, of free fermions on a discrete time lattice. So in this case, what happens is you encounter something that also happens in space, which is called fermion doubling. So what happens here? Something that's interesting about fermion doubling in this context is that you also get pi modes, and they emerge kind of very, very simply. So how does it happen? So you take your Schrodinger equation. I want to find the kernel of this Schrodinger operator. You replace your continuous time derivative with a discrete one, and then you can make an ansatz, which is that my wave function at time t oscillates with some frequency, call it p naught, and you know, I'm going to say this thing is an eigenstate of H. Okay, so I want to use the eigenstates of H to build eigenstates of the Schrodinger operator. And if you do this and you discretize time, what you find is that the energy and the frequency are related by this formula. Okay, so 1 over tau, which is my time lattice spacing, times sine of p naught tau is equal to E, where E is the you know, is an energy level of this H. And in the continuous time case, what you would find is p naught equals E, but here what you find is that they're related by taking this sign. Okay. Now, because there's a sign here, there's sort of two solutions for each E. There's one which is, you know, just get it, you get it by taking sine inverse of both sides. And then there's another one which is sort of pi over tau minus this solution. So for every E, there's two p naughts that you could assign. So this is called fermion doubling, and these extra levels here are called doublers. And one thing that you immediately see here is that if you have a discrete time theory with a zero mode, say localized on the boundary, there's going to be a pi mode as well. That happens automatically due to fermion doubling. One comment that I wanted to make before sort of proceeding and telling you what the talk is, sort of what we do in this talk, is that there's another sort of discrete time or sort of higher dimensional picture of Floquet systems that has been referenced several times in this conference, which is to take the Schrodinger operator and map it to a space-time lattice where instead of you know, real time, you have frequency. Okay, so this is a mapping that was developed many years ago, and you know, essentially, if you do this, so if you work, you know, if you try to formulate sort of an eigenproblem for the time periodic Floquet states, you get this Hamiltonian where, you know, H naught or Hn more generally is the nth Fourier component of your time-dependent Hamiltonian. So, you know, the way that you can think about this is that, you know, this is like a system in one dimension higher where, you know, on the sites I have, you know, a copy of my undriven system, and I have a static electric field in the sort of time direction, because, you know, if you keep going up or down along this diagonal, you add higher and higher multiples of the frequency. And then, for example, the first, the first Fourier component allows you to sort of absorb a photon from the drive and hop. Okay, so people have worked on thinking about, you know, equivalences between, you know, say d-dimensional Floquet systems and then d+1 dimensional systems in an electric field. Okay, so you can think about those types of systems, but what I'm talking about today is not this. It's really just taking time and discretizing it, taking your time derivative and making it a discrete derivative. So what are we going to do in this talk, or sort of the question that's motivating us, right? My colleague and I would like to understand one another when we talk to one another. So are pi modes in Floquet insulators the same as time doublers in lattice field theory? This is kind of the question that we were asking. And in order to, you know, not answer this question in full generality, but to sort of try to, you know, our approach is just take an example and see if it works, right? So this talk is going to be about how we developed an equivalence between the sort of spectra and phases of a Floquet model, and actually two time-independent discrete time models that are related to one another. The sort of general picture that emerges, so we start from some Floquet model that you can define on 2n sites. It has some SSH-like character. I'll show what it is on the next slide. So the spectrum of this thing can be mapped to the sort of discrete time spectrum of either a Sushri-Vertiger model, SSH model with half the sites, or Wilson-Dirac fermions with a quarter of the sites. Okay. Now, why do these guys have less sites than this guy? It's because you're putting back degrees of freedom when you do fermion doubling. So the static system has n sites in space, and then I do fermion doubling and I get back the states that I threw away. So this will hopefully become clear in the next few slides, but this is what we did. Okay, so for aesthetic reasons, we would like to end up or compare with sort of Wilson-Dirac fermions at the end of the day, because this is kind of a canonical thing in lattice field theory. So for aesthetic reasons, we will consider, instead of this sort of Majorana model that I showed on earlier in the talk, we consider sort of a complex fermion version of it. So we take a drive which has the same form. You drive with H0 and H1, and then H0 and H1 are still sort of a trivial and a topological Hamiltonian, but the sort of now everything is formulated in terms of complex fermions instead of Majorana fermions. So basically, H0 is the trivial SSH Hamiltonian. H1 is kind of the topological one. So we take this thing and actually you can your first question is, well, what is the phase diagram of this model? The answer is it's the same as the Majorana model for the following reason. So if you take your complex fermion and you write it in terms of two Majorana fermions, what you find is that you get sort of two chains. There's an alpha Majorana and a beta Majorana, and the couplings H0 and H1 map exactly onto those sort of Kitaev-like couplings that hybridize Majoranas within or between unit cells. So for example, this highlighted yellow chain is like one copy of the model that I showed a few slides ago. And then, then there's another copy here. And there's an additional kind of interesting feature, which is that, this obviously has a U1 symmetry that the Majorana model doesn't have, right? So there's actually some transformation rule that you can derive that sort of means that alpha and beta kind of rotate into one another under U1 symmetry. So it's kind of two copies of the model that are kind of, intertwined by symmetry in some interesting way. We don't really do anything with this, but it's an observation. What you get is the exact same phase diagram, except now your 0 or your pi modes are SSH-like complex fermion edge states rather than Majoranas. Okay, so how are we going to map these things onto one another? So our goal, sort of concretely, is we want to map the single particle quasi-energy spectrum, which I'll call epsilon, of UF, the Floquet operator, onto that of a static discrete time theory. Okay, so I do not want a discrete time theory that has a non-trivial time dependence. That's an interesting thing to consider, but I'm not going to consider it today. Okay, so this is my goal. And then how do we do that, right? So you can rephrase this goal as find a static Hamiltonian H whose doubled spectrum, this, right? So P naught is the sine inverse, or it's pi minus the sine inverse, right? So this is the doubled spectrum, and I would like P naught to be exactly, the set of P naughts that solve this equation to be exactly equal to the quasi-energies. And I would like the time lattice spacing tau to be equal to the Floquet sort of driving period T. Okay, so my goal is to find a Hamiltonian whose spectrum satisfies this. And one thing that you immediately notice is that if you have sort of a static discrete time theory, you automatically have to have sort of pi pairing of the single particle quasi-energies. Because if both of these equations are going to hold, that means that in the Floquet model, I had better have a situation where for every epsilon, there is also a pi minus epsilon. You need this in your Floquet theory to begin with, so you're already kind of restricting the type of system that you can be considering already, like if you want a static Hamiltonian at the end of the day. So then if you have this pi pairing, you can do the following trick. So you can take your quasi-energy spectrum, epsilon, and write it as the union of two pieces that I'll call epsilon tilde and sort of pi over t minus epsilon tilde. So I can take my spectrum and break it in half, okay? And that's really important because at the end of the day, I want to restore. So what I'm gonna do is I have to, now I just have a condition on these epsilon tildes, and these have to satisfy this equation. So I'm gonna identify epsilon tilde with these solutions, okay? So now there's epsilon tilde inside of the sign, and then the other ones are going to become the doublers, okay? So basically what I would like to do is take my model, find this epsilon tilde, and then look for a Hamiltonian whose spectrum satisfies this condition. So I have to take the sign of my quasi-energies, and then that is supposed to be equivalent to the spectrum of a static model, okay? Not obvious that this should hold, right? It wasn't clear to me that this should hold. It's not obvious that there's any model for which this would be true. Okay, turns out there is. So, and as I said, so this H has to have half the degrees of freedom of UF because the energies are associated with the epsilon tilde. So the epsilon tilde is the half of the spectrum that I'm keeping. Okay, so H has to have half the degrees of freedom of your original Floquet model. Okay, now as I said, this pi pairing is not generic. It happens in this model along this line that I drew. So if you take T naught, which is the amount of time that you evolve under the trivial Hamiltonian, if you fix this to pi over 4 in units of the driving period, which you'll probably hear me set to 1 unintentionally for the rest of the talk. If you park yourself here, you can show several ways actually, including by just calculating the quasi-energy spectrum, that you have this pi pairing along this line. Okay, so this, your Hamiltonian, it's tedious, but it's not, it's not terrible at the end of the day. You get out what the quasi-energy spectrum is. Okay, so our quasi-energy bands here take this form, so it's plus or minus cos inverse of minus cos 2 eta cos 2k. So k here is my my crystal momentum, my original lattice, and then what is eta? Eta is sort of a parameterization of where along this line I am. So here eta is basically T1 minus pi over 4. Okay, so that means that at eta equals 0, I'm sitting right at this transition, which by the way, this is the dual unitary point. And then if you go here, this is eta equals minus pi over 4. Here is eta equals plus pi over 4. So eta is the thing that I'm going to be tuning to cross this transition. So what does it look like? It looks like this thing on the left. And then I need to, the thing that I'm going to be interested in matching to a time-independent spectrum is not the quasi-energy itself, but the sign of the quasi-energy spectrum. So I'm plotting both the spectrum and its sign here. And then this blue highlighted region is what I'm going to take for my epsilon tilde. So I'm going to take as my epsilon tilde those quasi-energies corresponding to momenta between pi over 4 and 3 pi over 4. And then you can see that every quasi-energy here has sort of a corresponding partner at pi minus this value. So this is kind of symmetric here. So these extra guys here are going to become the doublers. Okay. So now the thing that we have to do is we have to find, what is this time-independent model? So natural thing to do as your first try is, well, I put in SSH to define my Floquet model. Maybe the Hamiltonian is SSH. That's like, we hope this, right? That would be great because otherwise, what are we gonna do? So this is our first try. So what is my SSH model? It is just the sum of H1, the topological part, and H0, the trivial part. U is the coupling that will associate with the topological part. So when U is bigger than V, this thing is in the topological phase. And then there's this dispersion that you can derive with periodic boundary conditions. And then the thing that you have to do is you have to solve that condition, right? So, and it turns out that if you take this expression and you take your quasi-energies, you take the sign and you sort of appropriately transform your momentum, right? Because, and sorry, this should be, oh yeah, this is right. So you remember, I'm choosing epsilon tilde to be quasi-energies corresponding to momenta between pi over 4 and 3 pi over 4. So I need to do some transformation on the momentum to map that to the Brillouin zone of the SSH model, which is 0 to pi. So it turns out that if you look at this formula, plug it in, do some algebra, this holds provided that U is equal to 1 plus or minus sine of 2 eta and V is equal to 1 minus U. Okay, so, and then you have this sort of plus or minus to resolve. So there's two solutions that, can't be distinguished by the bulk spectrum, okay? So if you do this, then, this is what I was plotting before. So if you now take this energy spectrum, put it on a discrete time lattice, what you get out are these bands. So these blue guys are the ones that came from here. And then these orange guys are the doubler modes, which you can check, this branch corresponds exactly to this, and this branch corresponds exactly to this. So an important note is that the spectra match, the dispersions don't. And you can get this by, you can see that the dispersions can't match because they, you're sort of changing the number of degrees of freedom. Okay, so you can show this, and then now there's the question of resolving this plus minus. How do you do that? Well, one natural thing is that you can sort of, if you say, okay, one of these branches has to be right, one of them has to be wrong, you can select the correct one by matching the topological phase of the SSH model to the topological phase of the Floquet model, okay? Topological phase of the Floquet model happens at positive eta. Remember, eta is my sort of tuning parameter. So this eta greater than 0 region should correspond to the topological phase of SSH. What's the topological phase of SSH? It's where this topological coupling, if you like U, is greater than V, or where the mass, which is the difference between the two, is positive, right? So if you compute the difference between these two things, you get plus or minus sine 2 eta, and then I want to choose the branch for which positive mass corresponds to positive eta. This is the positive branch, okay? So this is how I'm choosing the correct one, okay? So with this, you can you can sort of be confident that the Floquet and discrete time models have matching edge states. So at positive eta, the Floquet system has these 0 and pi modes, and then in the sort of discrete time case, you would get kind of modes that are localized to the edge, but then they have some either staggered sign change profile, or they're sort of constant in time along the boundary. Now, one thing that you might be skeptical of is, well, I'm only matching these things based on the sort of bulk periodic boundary condition spectrum, right? So they obviously should match exactly if I'm doing this. That's by construction. But then, really what we would like is also with open boundary conditions, the spectra should match. So as like a sanity check, you might expect there to be sort of 1/n finite size corrections when you use open boundary conditions. You're matching the edge states by construction, but hopefully the bulks match too. And indeed, you can even calculate this analytically if you want, but if you sort of park yourself at a positive eta and then examine sort of the maximum difference between the frequency spectrum of the discrete time Schrodinger operator and the quasi-energy spectrum of your Floquet model, and if you plot this thing, you see that you get 1/n pretty convincingly. So this tells you that in the thermodynamic limits, these spectra should be the same. And then you can ask, well, what about if I put in like a topological defect? Are the spectra still the same? Turns out they are. Okay, so what is a topological defect? Well, it's a domain wall in eta. So in the discrete time SSH model, it's sort of the familiar mass domain wall from Jakiv-Rebbe. So you have on one side U greater than V, on the other side V greater than U, and there's sort of one site that has, say, 2 strong bonds coming off of it. This is the domain wall. What about the Floquet system? So here, remember, it's a domain wall in an eta, so you still basically, you don't affect the sort of initial part of the drive, which is fixed. This T naught is pi/4 in some units, but in this second period where you evolve over T1, you basically weaken H1 across a particular bond. And then what you expect is, here there should be a localized 0 mode, and then here there should be a localized 0 and a localized pi mode. And indeed, if you do the same sort of test of the spectrum, you see the expected kind of 1/n behavior as well. So this kind of at least develops some, so this at least sort of allows us to imagine that there's some kind of equivalence between the Floquet and discrete time SSH models, in the sense that apparently kind of irrespective of boundary conditions or the presence of topological defects in the thermodynamic limit, the spectra are the same. So this is the result. And we're very happy about this because we put in SSH, we got out SSH. We weren't expecting that. It's not obvious if you just look at the quasi-energy spectrum that there's an SSH model anywhere. So we were happy about this. But then if you want more, right? You can also say, well, the sort of canonical model of lattice fermions is Wilson-Dirac fermions. So are these related to Wilson-Dirac fermions? And it turns out they are. But for those who want to see, what is a Wilson-Dirac fermion, you can define it with this Hamiltonian. So there's your sort of usual, discrete spatial derivative that corresponds to your, this is your sort of lattice, momentum, if you like. And then there's an extra term here that depends on the second derivative, which is called the Wilson term. And I should say these psi's now are two-component Dirac fermions. Rather than, so now instead of two sites in a unit cell, we have one site in a unit cell, but there's a spin. Okay, and the purpose of this Wilson term, like its whole purpose in life, is to remove fermion doubling in space. So this is the spectrum of this model, and the reason that people find this useful is that, for example, if you set m equals 0 to make your sort of massless fermion, you only get a 0 here. You don't get a zero at pi. Right? And that's what would happen if you had m equals 0 and no r. Okay, so the reason that this thing exists is to remove this extra fermion that you would get over here. So this thing is there because they don't want fermion doubling in space. This is one way of handling fermion doubling. There's also, another approach, which is like staggered fermions, similar to SSH. This thing also, it turns out, has edge modes. So with open boundary conditions, you can sort of do a little calculation. And what you find is that when m, the mass, is less than 0, there's a localized edge mode with this localization length. Okay, so only when m is less than 0 is this thing decaying, basically. This all sounds a lot like SSH. That's not really a coincidence. This spectrum is exactly the same as the SSH spectrum upon re-identifying some parameters. And as I said, that you can imagine that this is because you're basically taking your sublattice and then viewing it as a physical spin. Okay, so now we can do the whole same song and dance, and as you might expect, it goes through because this spectrum is the same as SSH. So you take these ingredients, your Wilson-Dirac, I almost said Bigger Dyson, sorry, Wilson-Dirac spectrum, and then your quasi-energy spectrum, and then plug it into this formula, you get out an answer. And what you find is now the mass is again, plus or minus sine of 2 eta. How are we going to fix the sign? We're going to fix the sign by demanding that m be negative when eta is positive now. Okay, so this means that m has to be negative, so we pick the minus branch. Okay. So this is sort of demonstrating that this sort of canonical lattice fermion model is actually also, you can think of it as equivalent to the Floquet model, with the same caveats about finite size corrections and taking the thermodynamic limit. Okay, so to summarize, what have we done? So the 1D Floquet SSH model for a particular T naught is equivalent to two discrete time lattice fermion theories, SSH and Wilson-Dirac. Equivalent how? Equivalent in the following sense. The spectra match exactly with periodic boundary conditions due to this mapping, and they match in the thermodynamic limit with open boundary conditions and domain walls. There's this sort of, because you're sort of getting the quasi-energies you throw away back via fermion doubling, the corresponding discrete time SSH model has n spatial sites if the original model had 2n. And then because these fermions are spinless, these fermions are spinful, you need n over 2 sites for the Wilson-Dirac model. And so, we now at least have one case where we know that pi modes in Floquet and discrete time are the same thing. Okay. Now, this is obviously nice, but one has to also confront the fact that there's a whole remainder of the phase diagram to explore, right? So does that mean that the 0 and pi phases can't be captured? Well, one thing to note is that you can have pi pairing elsewhere. So for example, if you have periodic boundary conditions, there's actually pi pairing along this line too. The reason is that there's a unitary transformation that involves, that basically exchanges T0 and T1. It involves a one-site translation that maps H0 and H1 into one another. But obviously the spectra with open boundary conditions are not the same, because when you can have a 0 mode with no pi mode and vice versa. Okay, so how do you remedy this? We have some ideas. It's clear that you can't do this with just a time independent Hamiltonian. So this is the question that we're now investigating. And then sort of in terms of other things to do next, there's a lot of interesting Floquet topological invariants. Clearly, there's been a lot more since these works. We heard about them during the nice pedagogical lecture. But there's also, sort of space-time lattice topological invariants. There's Chern numbers you can calculate just on that space-time lattice. You can ask, are those the same as the Floquet topological invariants for these models? It would be, that would be an interesting thing to check. Another thing is, this picture that I kind of was using to motivate why Floquet systems are interesting at the beginning of the talk. These anomalous sort of topological insulator edge modes. Can this actually be modeled as a space-time lattice fermion theory? And if it can be, is it still Wilson-Dirac, or is that an accident of 1D? And then, of course, the thing that you would like to do is to add interactions. And then you can ask, well, we know that Floquet becomes very hard when you add interactions, you get heating. And if there is any notion of kind of similarity between the sort of lattice and Floquet problems, how does, for example, heating manifest itself in the lattice formulation? Does it tell us something about instabilities of the system with strong interactions, or what does it tell us? Does it tell us anything? So yeah, with that, that's my time, and thank you very much. Okay.
I think I have a way to construct this time independent. So something is wrong with my understanding. So that's why I'm asking. Mm-hmm. So naively, I would say, if I understand correctly, what you're trying to find is an Hamiltonian such that a discrete application of it will be the same as a period of your periodic drive.
Yeah, so not exactly this.
Yeah. So that the spectrum is the same.
Yeah, I think it's not. I mean, so what you're describing sounds more like the Floquet Hamiltonian,
right,
which we.
Exactly.
Yeah,
so
yeah.
What is the difference between the logarithm of the Floquet Hamiltonian and your discrete?
Yeah. So the answer is that the spectra simply are not the same. Like, so it's precisely like you have to take. Let me find my my picture here. So you have to, so these are my, this is like, cos inverse of blah, blah, blah. This is my Floquet spectrum, right? This is not like, if you just isolate this part of the spectrum, these are not SSH bands. They are SSH bands after you fermion double, right? So I mean, so that's the thing that's the thing that's so, and it's because the reason is that you're not looking for a Hamiltonian that generates stroboscopic evolution. You're looking for a Hamiltonian whose spectrum, when you discretize the derivative operator, the time derivative operator in the Schrodinger equation, that gives you where the spectrum of that operator matches the spectrum of the Floquet system. That's what you want to do, and that's why you have to sort of take the sign. Taking the sign is important. Well, I mean, it's different. I mean, simply, so, you're not now, so the problems are different. I mean, you're not, sorry, let me find my Schrodinger operator. So what you're trying to do is look at the spectrum of this guy, and it's not, the exponential of this guy is not generating any, like if you just take this guy and discretize it, this guy is not generating stroboscopic evolution. So it's really, this is the object that you're interested in when you're putting like a lattice field theory on a computer. You're looking at the spectrum of this operator, usually actually in Euclidean time. Yeah. So it's just a different. So literally, it's you're taking your system, and then you are discretizing this thing, and then the sort of kernel of this operator is what you're interested in now.
Yeah.
Yeah, I think.
Okay. So yes, thank you very much for this very interesting talk. So what happens to the pi mode? Does it survive this transformation, and what is its relevance for the continuum going back? Okay, going back again. So you take discrete time of something, and if you take the continuum limit of that, if it does, provided my answer to my question is yes, what does it mean for the continuous time model? I have another question.
Sure. Okay. So to answer the first question, so you lose the pi mode in the continuum. The pi mode comes precisely because instead of having sort of an unbounded you're basically it's only because you're going to it's only because you discretize the derivative that you get the pi mode. So the pi mode, you need the sign to get the pi.
I see.
Yeah.
And so I have to admit, I'm having trouble now seeing interactions fitting into this picture precisely because of heating, right? I would assume.
Right. Yeah. So there are things that you can. I mean, that's absolutely true. I also have trouble imagining how it works. One thing that you could imagine, though, is that what we're looking at here, like these P naughts, are for this Dirac problem, right? The Dirac propagator is the inverse of the Schrodinger operator, right? So you could imagine you start from sort of non-interacting Green's functions, and you've matched the poles. And then now the question is like, self-energies and things like that.
No, but physically, I mean, would this mean somehow that if I evolve with this discrete time theory, that I would expect it also to heat, or is there no connection?
Well, it could represent, I mean, of course, you have to be careful, like the quantities that you're comparing. So, you can maybe make a statement about, for example, the propagator in the presence of interactions, which is not necessarily the same as heating, but perhaps you could identify, I think, instabilities or something in the presence of interactions this way. There's a question of interpretation that we haven't resolved, but we're interested in.
Okay,
Yeah.
Thank you very much.
Even connected to kind of those questions, I was wondering, is this kind of the most trivial kind of discretization of the time evolution operator or the derivative, right? So for Laplace operators, people have kind of studied a lot, what you should do, how you should preserve symmetries.
Yeah.
Have you thought about kind of higher order discretizations? Does it change the whole story? Do we get Fermion quadrupling?
Yeah, right. So the story that I'm aware of, and I must admit that my background in lattice field theory, like I'm leaning on my colleagues' tree for this a lot. But what I do know is that if you use the forward or the backward difference, for example, your Schrodinger operator is not Hermitian, and that's a problem. So that's what motivates this. Now, if you use some higher order discretization, I don't know if that's actually something that people used. Perhaps it becomes more useful, like in interaction, in the presence of interactions. I'm not really sure. Yeah.
Then your tau is fixed by the t, right? So in some sense, of course, for large t, then of course I don't actually solve the right evolution, so I could expect anything. Like heating wouldn't be surprising if I actually don't solve the proper time evolution, right?
Yeah. Great.